This is the Math 680 review session for the list of problems that we will be doing today. Hopefully you can see it here. We'll be doing in order these problems from Ross, then in this order these problems from the additional homework problems. So if you want to jump around the video, you'll know exactly the order in which we'll be doing the problems. And again, in addition to this particular video, I'll have the individual sheets that I've written up, put up at D2L as a PDF file, like we've done in the past. So let us begin with 17.9 B and C. So 17.9 is the following. Prove each of the following functions. Again, let me number the page here. This is 17.9 B and C. So starting with B. Prove the following function is continuous by verifying the epsilon delta property. So the function here is f of x equals the square root of x, and the point is 0. So we want to show the square root of x is continuous at 0. So let's take a look. And again, obviously, if we're looking at 0, we're only looking at 0 and the right side of 0, because to the left of 0, the square root of x doesn't exist. So for scrap work, we're looking at f of x minus f of 0, and somehow we need this to be less than epsilon. And what we can control is we can keep x as close to 0 as we want. So for the scrap work, this is the square root of x minus 0. So I'll write it as the square root of x. And we want this to be less than epsilon. So this is, and again, what we can do is we can keep x as close to epsilon as we want, rather x as close to 0 as we want. We're going to want this to be less than epsilon. And there's the question. Well, we're only going to be looking when the absolute value of x minus 0 is less than epsilon, or the absolute value of x is less than delta. This is going to be a little bit on the tricky side, but this is saying that the absolute value of x to the 1/2, or the square root of x, is less than delta to the 1/2. So if the square root of x is going to be less than delta to the 1/2, and we want this to be less than epsilon, the way that we can do this is let epsilon be less than, rather let delta be less than epsilon squared. So again, we're looking at f of x minus f of 0. That's the square root of x. How do we get this less than epsilon? Well, if the absolute value of x is less than delta, then the absolute value of x to the 1/2 is less than delta to the 1/2. How can we get delta to the 1/2 to be less than epsilon? Well, we can just let delta be less than epsilon squared. I'm trying to think about whether there's an easier way to do this. There would be if we weren't taking the point at 0, but we are. So now, here's the proof. And this is not your typical epsilon delta proof. If I'm asking you for an epsilon delta proof, I'll be having you work with a rational function, or more likely a polynomial. You won't have to worry about square roots. So the proof, given epsilon greater than 0, let delta be less than epsilon squared. Then, whenever the absolute value of x minus 0 is less than delta, the above inequalities show that the absolute value of f of x minus 0 is less than epsilon. Therefore, f of x is continuous at, let me put this up where you can read it, is continuous at 0. So given epsilon greater than 0, let delta be less than epsilon squared. Then whenever the absolute value of x is less than delta, the above inequalities show that f of x minus 0 or f of x minus f of 0 is indeed less than epsilon. Again, this is true because we're just plugging in for f of x and f of 0. This is true from this computation over here, and this is true by our choice of delta. So that's 17.9b. Next, for 17.9c, we're looking at f of x equals x sine 1 over x. At least this is the case when x is not equal to 0. And it's equal to 0 when x is equal to 0. And we want to show that we have continuity at 0. So for the scrap work, again, we have f of x minus f of 0. And we want this to ultimately be less than epsilon by controlling our choice of delta. Well, this is x sine 1 over x, because that's f of x, minus f of 0. But this is the absolute value of x times the absolute value of sine of 1 over x. But the point is, values of the sine always have absolute value less than or equal to 1. So this is less than or equal to the absolute value of x. We're only going to be taking points where the absolute value of x is less than delta. And we want to know how to get this less than epsilon. Well, this just says let delta be less than epsilon. So, for the proof, given epsilon greater than 0, let delta be less than epsilon. Then, whenever the absolute value of x minus 0 is less than delta, the above inequalities show that the absolute value of f of x minus f of 0 is less than epsilon. Again, let's check. This is true because we just substituted in for what f of x is and what f of 0 is. This is true because just properties of the absolute value. This is true because the absolute value of the sine is always less than or equal to 1. This is true because we're only looking at points where the absolute value of x is less than delta. And this one is true because we chose delta to be less than epsilon. So again, that's the proof that this particular function is continuous at 0. Again, these two problems are, they're interesting problems, but I think it's more natural for me to give you things like polynomials or maybe rational functions. So that takes care of 17.9. Let's move to 18.3. That's the next one. So this is now page 3. The problem is 18.3. So let's see what's going on here. For 18.3, use calculus to find the maximum and minimum values of x cubed minus 6x squared plus 9x plus 1 on the interval from 0 to 5, but, so this is x cubed minus 6x squared plus 9x plus 1 on the half closed, half open interval. And in some sense, this is kind of a trick question because since this interval is not closed, and we don't have to worry about continuity here because this is a polynomial, but since this interval is not closed, there's not a guarantee that there is a max or a min. Now, the focus might be a little bit funny here, so let me see if I can adjust the focus. Hope that worked well. So let's see what happens on the closed interval from 0 to 5. Because we know on that interval there is guaranteed to be a max and there is guaranteed to be a min. And let me just check one more time if I can work the focus a little bit better. I hope that's better. So f prime is 3x squared minus 12x plus 9. And remember, our candidates are going to be the endpoints. So we'll have to look at f of 0. We'll have to look at f of 5. And the other candidates are where the derivative is 0. Well, if 3x squared minus 12x plus 9 is equal to 0, dividing out by 3, that means x squared minus 4x plus 3 is equal to 0. This looks like it factors as x minus 1 and x minus 3. We get x equals 1, x equals 3. Both of them live inside the interval, so we have to consider them. So when we plug in, f of 0 is 1. F of 5, well, that's going to take a little bit of work. 5 cubed is 125, minus 6 times 25, that's minus 150, plus 9 times 5 is plus 45, plus 1. Let's see, this is negative 25. If you add 45, this is negative 25. Add 45, you're plus 20. Add 1, you're plus 21. F of 1 is 1 minus 6, so that puts me at minus 5. Plus 9, that puts me at plus 4. Plus 1 gets me to 5. Let's check that again. 1 minus 6 is minus 5. Plus 9 is plus 4. Plus 1 is plus 5. And when you plug in 3, 3 cubed is 27. Minus 6 times 9, so that's minus 54. Plus 9 times 3, that's plus 27. Plus 1, so you get, again, 27 minus 54 plus 27 plus 1. That comes out to be a 1. So what we get is the minimum value is 1 occurring at 0 and at 3. So there is a minimum. The problem is the maximum value here occurs at a point, well, for this interval, the maximum occurs at 5. But for this particular interval, 5 doesn't exist. So what we have is a function which is increasing up to a value of 21. So when you plug in 5, you get a value of 21. So again, when you plug in 5, you get a value of 21. But if you weren't allowed to plug in 5, you can get all numbers approaching 21. So in other words, if you're on the interval from 0 to 5 and it's open at 5, by plugging in points as close to 5 as you want, you can get values as close to 21 as you want, but there is no maximum because any value you get close to 21, you can always get a bigger one. So this is sort of a trick question. This one has no maximum because you can get values as close to 21 as you want. So in some sense, it's kind of a trick question, and I think it even says that in the back of the book. It's a trick question because I asked you for the max and the min, but there was no maximum. So that takes care of 18.3. Moving on to, I think I'm on page 4. Moving on to page 4, people were interested in 18.5, A and B. So for A, let f and g be continuous functions on the closed interval AB such that f of A is big. So we're looking on the closed interval from A to B. and we're dealing with continuous functions, f of a is bigger than or equal to g of a, and f of b is bigger than or equal to g of b, and we want to prove that there's some point on the interval such that f and g are the same. Well, if you think about a picture isn't a proof, but it's awfully helpful. When you plug in a, f is on top or equal to g, but when you plug in b, g is on top of or equal to f. Well, so the graph of f is going to be something like this. The graph of g is going to be something like this. And the point is, if f starts on top and finishes on the bottom, it seems pretty clear that at some point in the middle, f and g are going to be the same. Now, how do we go about proving this? Well, if you think about it, if f starts off on top, then f minus g is positive. If f ends up on the bottom, then over here, f minus g is negative. So the function f minus g changes sign. So for the proof, you let h of x equal f of x minus g of x. The given here says that h of a is greater than or equal to 0. It says h of b is less than or equal to 0. So here's the situation. It's possible that you're 0 at one of the endpoints. So if h of a equals 0, or h of b equals 0, we're done. Because if h of a is equal to 0, that's a point where f and g are the same. If h of b is equal to 0, that's a point where f and g are the same. So, final case, suppose h of a is not equal to 0 and h of b is not equal to 0. Well, that means that if h of a isn't 0, h of a is positive. If h of b isn't 0, that means h of b is negative. That means that h changes sign. And h is the difference of two continuous functions, so h is continuous. So here you have a continuous function that goes from positive to negative. So the intermediate value theorem says there exists, I'll call it C, some C in the open interval such that h of c is equal to 0. But that's the same as saying that f and g are equal at c. Okay, so here's the point. If you want to show that f and g are equal at some point, look at the function f minus g, and that's the same as showing that that function at some point is equal to 0. If they're 0 at either of the endpoints, you're done. If they're not 0 at the endpoints, then h changes sign. And if h is continuous and changes sign, then you get a point in the interior of the interval from the intermediate value theorem that makes h 0, but that's the same as making f and g the same. So things change signs, so by the intermediate value theorem, there's a point that makes f and g the same. Now, show that example 1 can be viewed as a special case of part A. Actually, I'm not quite sure what example 1 says, but again, I think the point is that if you understand 18a, that's the key to the problem. Moving along, next one is 18.7. I want to mess up my numbering here. This is moving to page 5. 18.7. 18.7 says, prove that x e to the x equals 2 for some x in the open interval 0, 1. Well, let's take a look at both sides of this here. When x is equal to 0, this side is equal to 0, and this side is equal to 2. So the right-hand side is the bigger one. When x is equal to 1, the left-hand side is e, and the right-hand side is still 2. The right-hand side is bigger 1. So notice, this used to be the bigger one. Now this is the bigger one. That means if you look at the difference of these, there's going to be a change in sign. So this is going to be basically the same exact argument as moments before. Let h of x equal x e to the x minus 2. Notice h of x is a continuous function. H of 0 is negative 2, which is certainly less than 0. H of 1 is e minus 2, which is more than 0. So in other words, the continuous function h changes sign. It goes from negative to positive on the closed interval 0, 1. So the intermediate value theorem says there's some point in the interior such that h of c is equal to 0. But h of c being equal to 0 says that e to the c minus 2 is 0, or c e to the c is equal to 2. So again, the main idea, just like the previous problem, so these are very complementary problems. If you look at the difference of these two functions, it's still continuous. It goes from negative to positive, so it changes sign on the closed interval. So the intermediate value theorem says there's some point in the open interval that makes the function equal to 0, but making the function equal to 0 is exactly making these two equal. So once again, another use of the intermediate value theorem. That takes care of 18.7. Next question, moving to page 6. Next question was 19.3, A and B. So for 19.3a, we want to show that the function, so this is a, that the function x over x plus 1 is uniformly continuous on the closed interval 0, 2. So that means we want to show that we can make any two values of this function as close to each other as we want just by plugging in numbers that are close to each other. So for the scrap work, let's look at the difference of two values of the function, f of b minus f of a. And we want to show that we can make this as small as possible just by keeping the distance between b and a as small as we want, because that's what we can control, how far b and a are from each other. Well, plugging in, we get b over b plus 1 minus a over a plus 1. Let's do some algebra. Common denominator, b plus 1 times a plus 1. When we combine this and look at the new numerator, this would be b times a plus 1, so ba plus b. B plus 1 times a, and we're subtracting, so that's minus ba minus a. So The numerator is a b minus a. Well, that's exactly the thing we're looking for. We want to factor out an absolute b minus a, because we can make this as small as we want. Then what's left over is 1 over the absolute value of b plus 1 and 1 over the absolute value of a plus 1. So this we can make as small as we want. But what can we say about this? Well, a and b are both in the closed interval from 0 to 2. That means a plus 1 and b plus 1 are both in the interval from 1 to 3. So in particular, a plus 1 and b plus 1 are bigger than or equal to 1, which means 1 over a plus 1 and 1 over b plus 1 are both less than or equal to 1. So as long as we're in the interval from 0 to 2, this is less than or equal to 1. Everything in sight's positive, so don't worry about the absolute values. This is also less than or equal to 1. So this is less than or equal to the absolute value of b minus a. Well, bingo, we're almost there, because this is what we can control. This is going to be less than delta, so that's going to be less than delta. And we want this to be less than epsilon, and that's simply let delta be less than epsilon. So here's the proof. Given epsilon greater than 0, let delta be less than epsilon. Then, whenever the absolute value of b minus a is less than delta, in other words, as long as we plug in 2 points that are close to each other, we have that the absolute value of f of b minus f of a is less than epsilon. Well, again, let's check. This equality holds because we just plugged in. This equality holds just from basic algebra. This equality holds because we can just use properties of the absolute value. The key thing is that on the interval from 0 to 2, this is less than or equal to 1. This is less than or equal to 1. So this is less than or equal to the absolute value of b minus a. Again, what you want to do is be able to factor b minus a out, because this is going to be less than delta, and this is less than epsilon because of the choice that we made for delta. So again, here's your proof, and then, so therefore, f of x is uniformly continuous on the interval from 0 to 2. The key part of the proof is, again, that this piece and this piece are both less than or equal to 1. It doesn't matter what number you have them less than or equal to, as long as you can come up with some inequality. I mean some bound, and they're both bounded by 1. 19.3 Part B should be sort of similar, so that'll be a good thing to reinforce this. So I believe this is now page 7. And now what we're trying to show is uniformly continuous is f of x equals 5x over 2x minus 1, and it's going to be in the interval from 1 out to plus infinity. So again, what we want to do is we want to show that any two values of this function can be made as close to each other as we want, just by keeping the numbers that we plug in close to each other. So for the scrap work, let's look at the absolute value of f of b minus f of a. So we're measuring how far apart two values of this function are, and what we like to do is factor out a b minus a and bound the rest. So plugging in, we get 5b over 2b minus 1 minus 5a over 2a minus 1 And this is equal to, well, common denominator, 2b minus 1, 2a minus 1. When we do the cross multiplying here, this is going to be 10ba minus 5b. This is going to be a negated 10ba, and again, minus negative 5a, so plus 5a. So the 10ba and then the negative ba cancel, and this is going to be negative 5b plus 5a. Well, when you take the absolute value of that, that's 5 times the absolute value of b minus a. Because again, this is actually 5 times a minus b, but a minus b and b minus a have the same absolute value, times 1 over the absolute value of 2b minus 1, times 1 over the absolute value of 2a minus 1. Now, we can make this as small as we want. That's just a constant. If we can bound this and bound that, we'll be in great shape. Well, here's what we know. A and b are in the interval from 1 out to plus infinity. That means 2a and 2b, trying to see what these things look like, are in the interval from 2 to infinity. That means 2a minus 1 and 2b minus 1 are in the interval from 1 to infinity. So this 2b minus 1 is greater than or equal to 1. This 2a minus 1 is greater than or equal to 1. So that says 1 over 2a minus 1 and 1 over 2b minus 1 are always, well again, since these things, the numerators, rather the 2a minus 1 and 2b minus 1 are greater than or equal to 1, if you put them in the denominator, you get a fraction which is less than or equal to 1. Again, the point is, this is always greater than or equal to 1. This is always greater than or equal to 1. So these fractions are less than or equal to 1. So this is less than or equal to 5 times the absolute value of b minus a. I'm only plugging in points where b minus a differ by at most delta. So this is less than 5 delta. We want this to be less than epsilon. How do we do this? Well, we just let delta be less than epsilon over 5. And so now here's your proof. Given epsilon greater than 0, let delta be less than epsilon over 5. Then, nice word I invented, then, whenever the absolute value of b minus a is less than delta, the above inequalities show that the absolute value of f of b minus f of a is less than epsilon. And again, let's see why this is true. We want this to be less than epsilon. Well, this equality holds because we just plugged in, we basically used the definition of the function. This equality holds just from doing some algebra. This equality holds, again, just from doing some algebra, and the key things is you pulled out a b minus a, which you can completely control. You just want to bound the rest. Since a and b are bigger than or equal to 1, these fractions are less than or equal to 1, because we did that computation here. Since this is less than or equal to 1, this inequality holds. We're only looking at points where the absolute value of b minus a is less than delta. That's why this holds. And since we chose delta to be less than epsilon over 5, that's why this one works. So, as long as you keep a and b within epsilon over 5 of each other, their values will be within epsilon of each other. So there's 19.3. The last question that people submitted from Ross is 29.1 A, C, and E. So what we want to do is determine whether the conclusions of the mean value theorem hold, meaning there's a point where the derivative is equal to the average rate of change on the specified interval. If the conclusion holds, give an example that makes it work. If it fails, on which hypotheses of the mean value theorem fail. Okay, so here are our examples. X squared on the interval from -1 to 2. Absolute value of x on the same interval, and 1 over x on this interval. Okay, here are some guarantees, things that you can go to the bank with. Continuous and differentiable everywhere, so on a closed interval, we can apply the mean value theorem. This function is continuous and differentiable as long as you stay away from 0. We're looking at the interval from 1 to 3, so this is continuous and differentiable, so the mean value theorem will hold. In other words, there will be at least one point here where the derivative is equal to the average rate of change. There'll be at least one point here where the derivative is equal to the average rate of change. This one we'll worry about later, because notice there's a point where it's not differentiable. It's not differentiable at 0, so the mean value theorem doesn't apply. But it's still possible that there's a point where the derivative is equal to the average rate of change. We can't apply the mean value theorem. There's no guarantee that there's a point here where the derivative is the average rate of change, but there might be one. So for the first one here, look at f of 2 minus f of minus 1 over 2 minus minus 1. This is the average rate of change here. So this is going to be 4, because I'm squaring 4 minus 1 is 3, over 2 minus minus 1 is 3. So the average rate of change of this function, the interval from -1 to 2, is 1. Again, if I did all the arithmetic right. Now, mean value theorem guarantees there's some point where this is equal to the derivative. The derivative is 2x. So when does this happen? This happens when x is equal to 1/2. So for this one, the mean value theorem applies, and at x equals 1/2, the exact rate of change is equal to the average rate of change. Again, this is the exact rate of change because it's the derivative. This is the average rate of change because we just computed it. And at 1/2, the exact rate of change equals the average rate of change. For the third one on this page, because we know the mean value theorem applies, we have, again, f of 3 minus f of 1 over 3 minus 1. Well, f of 3 is 1/3. F of 1 is 1 over 3 minus 1 is 2. Let's see, so this is 1/3 minus 1 is -2/3. Divided by 2 is -1/3. So there's some point where the derivative is guaranteed to be -1/3. Well, let's see what the derivative is. The derivative of x to the -1 is -x to the -2, or -1 over x squared. So here is the average rate of change. Here's the exact rate of change. We have to figure out when these are equal. Well, they're equal when x squared is equal to 3, but it has to be a point in the interval. Well, x squared is equal to 3 at plus the square root of 3 and minus the square root of 3, but only plus the square root of 3 lives in this interval, because the mean value theorem guarantees there's a point in this interval where the exact rate of change equals the average rate of change. So in the interval, the answer is x equals the square root of 3. Because again, this is true at plus or minus the square root of 3, but we have to take a point in the interval. So notice when x is the square root of 3, you've taken a point in the interval where the exact rate of change equals the average rate of change. Now, so again, in part A and part E, the mean value theorem guaranteed there was a point where the derivative was the average rate of change, and we went ahead and found it. For part C, there are no guarantees that there is a point where the exact rate of change equals the average rate of change. Coincidentally, there might be a point where it happens, but the mean value theorem doesn't guarantee it. Now, if you think about the absolute value function, the derivative is plus 1 on the right-hand side and negative 1 on the left-hand side. So the derivative of this function, depending upon where you are, positive or negative, the derivative is going to be plus 1 or minus 1. But let's see what the average rate of change here is. We're looking at f of 2. Well, we'll look at it if I can show it to you. F of 2 minus f of negative 1 over 2 minus negative 1. Well, for the absolute value function, f of 2 is 2, f of negative 1 is 1, 2 minus negative 1 is 3. This is 1/3. So the average rate of change of the function is 1/3. But notice, there's no point where this is equal to the derivative, because for all the points on the positive side of 0, the derivative is plus 1. For all the points on the negative side of 0, the derivative is negative 1. So the derivative, so f prime, is never equal to 1/3. Now, we couldn't apply the mean value theorem. Why can't we apply the mean value theorem? Because the mean value theorem applies if you're continuous and differentiable, but lo and behold, there's one point where this function is not differentiable. It's always continuous, but there's one point where this function is not differentiable, namely at 0. So that takes care of 29, and that takes care of the problems from Ross. So now that we're done with the problems from Ross, now let's look at the additional homework problems. First one that was asked was 2C, and it's using the definition of continuity, show that g of x, which is 4x cubed minus 2x plus 1, is continuous at negative 3. So for the scrap work, we have to show that we can keep g of x as close to g of negative 3 as we want, just by keeping x close to negative 3. So somehow, and this is easy, these are polynomials, these are things you should be able to handle in the exam, we need to factor out an x minus negative 3 from here, or factor out an x plus 3. Well, g of x is 4x cubed minus 2x plus 1. G of negative 3, well, let me get the calculator out for that one. Now you actually have all this stuff on the solutions that I sent you, but we're looking at the function 4x cubed minus 2x plus 1. So 4x cubed minus 2x plus 1. What we're plugging into it is negative 3. So I'm going to plug negative 3 into the function, and the calculator gives me an answer of negative 101. So this is now the absolute value of 4x cubed minus 2x, and this is a plus 1 minus 101, which is the same as adding 101. So this is plus 102. And the idea is one should be able to factor out x minus negative 3 or x plus 3. So I should be able to factor out an x plus 3. And then by long division or synthetic division or however you want to do it, you should be able to factor an x plus 3 out of 4x cubed minus 2x plus 102. Now, this will not be an exciting thing to watch of me actually factoring x plus 3 out of this. But let's see, the leading term has to be 4x squared. The constant term multiplies by 3 to get 102, so it's 102 divided by 3, which is 34. Now, to get the x term, this gives me 34x, but the answer is negative 2x here. So if it's plus 34x, to get to negative 2x, I need to subtract another 36x. So I shall multiply this by minus 12x. And let me just I will just check on the calculator that this really is the correct factorization. So I'm claiming that 4x cubed minus 2x plus 102, you factor out the x plus 3, and you get, if I did the algebra correctly, 4x squared minus 12x plus 34. So again, what I'm doing is I'm comparing on the calculator. It's hard to see. I'm comparing on the calculator 4x cubed minus 2x plus 102, and I'm comparing it to x plus 3 times 4x squared minus 12x plus 34. I'm going to check if I indeed are getting the same answers for these. And let's see. Something's a little funny with the calculator in that it won't give me an answer. So again, let's check on the calculator. And these two things do indeed turn out to be the same. So again, that's not the most exciting thing in the world, but here's my 4x squared minus 12x plus 34. I can make this less than delta, where delta is as small as I want, so all I need to do is bound this. So to bound this, let's say, let delta be less than 1. That means that x is staying within 1 unit of negative 3. So again, that means x plus 3 is between 1 and negative 1. That means x is between negative 2 and negative 4. And the key thing is I want to bound the absolute value of x. So the absolute value of x, well, when x is between negative 4 and 2, the absolute value of x is always bounded by 4. So here's the key. Triangle inequality says that this piece is less than or equal to 4 times the absolute value of x squared. Again, I'm taking the absolute value of this piece, so it's plus 12 times the absolute value of x plus 34 times the absolute value of x plus 3. Now the absolute value of x is less than or equal to 4. So this is less than or equal to 4 times 4 squared plus 12 times 4 plus 34 times the absolute value of x plus 3. Well, let's figure out what this is. This is 4 cubed, so that's 64. This is 12 times 4, so that's 48. That's a 34. So that comes out to 146. So this is less than or equal to 146, the absolute value of x plus 3. So let's see what's really going on here. What's really going on here is this measures how far x is away from negative 3. This measures how far the function is from g of negative 3. And this is saying the function wanders at most 146 times as much as the variable moves. So again, whatever change you get in the variable, it's magnified by at most 146 times to see what the change in the function is. But as long as I have a number here, it doesn't matter what this number is, but getting a number here is what I need, because this is going to be less than 146 delta. And how can I get this less than epsilon? I just let delta be less than epsilon over 146. Again, assuming I did all the arithmetic correctly. You can double check on the solutions that I had sent you during the week. So now here's the proof. Given epsilon greater than 0, let delta be less than, well, in order for the absolute value of x to be less than 4, that came from delta being less than 1. For this piece to be true, it came from delta being less than epsilon over 146. So I need both of these things to be true. So if I need delta to be both less than 1 and less than epsilon over 146, just let it be less than the minimum of 1 and epsilon over 146. Then, whenever the absolute value of x minus negative 3 is less than delta, we have, well again, let's notice what we have. We have this is true because we just plugged in. This is true again because we just plugged in. This is true because we factored. This is true because of the triangle inequality and the fact that the absolute value of x is less than or equal to 4. Again, this is true because the absolute value of x is less than or equal to 4. This is true from basic arithmetic. And this is true, this one is true because we're just looking at points where absolute x minus negative 3 is less than delta. And this is true because delta is less than epsilon over 146. So whenever the absolute value of x minus negative 3 is less than delta, we have the absolute value of g of x minus g of minus 3 is less than epsilon. Therefore, g of x is continuous at x equals negative 3. So that takes care of 2a. Next questions were on 3a and b. So we have a function defined differently on rationals and irrationals. It's 7 if x is rational, and it's 23 when x is irrational. Okay. We want to show that for any rational number you pick, the function is not continuous there. And then we want to show for any irrational number you pick, the function is not continuous there. Well, here's the point. In part A, we're looking at the point where a is rational, and we want to show that h is not continuous there. Well, the point is, the function is giving you a value of 7. But no matter how small an interval you take near the point A, not only are you going to be plugging in rationals, but you're going to be plugging in irrationals. So no matter how close you stay to the point A, you're sometimes going to be getting values of 23. That means you can't keep all the values of your function close to 7. If you were continuous, since h of a is equal to 7, then by staying close to a, you should keep all the values of your function close to 7. But you can't, because all of these values are far away. Now, how far away are these things? 16. So, no matter how close you are to a, this function is going to keep spitting out values 16 units away from here. So, epsilon is how close you want to be. Notice you can't stay within, say, 1 unit of 7, or 5 units of 7, or 10 units of 7, because here you keep on wandering 16 units away from 7. So, here's the proof. Let epsilon equal 1. Okay. For any choice of delta greater than 0, there will be an irrational x such that the absolute value of x minus a is less than delta. In other words, no matter how small an interval you pick, you can find a point that's close enough to a that is irrational. So then what we have is the absolute value of h of x minus h of a. Since x is irrational, it's giving you a value of 23. Since a is rational, it's giving you a value of 7. So in other words, you're getting points close to a that when you plug in gives you values of the function 16 units away from 7. Well, that's certainly bigger than the number 1, which was epsilon. So if you're continuous for every epsilon, you can find a delta. Well, for this particular epsilon, no matter what delta you try, there's an irrational x that's within delta units of a that pushes the function 16 units away from 7. So it's not within epsilon units of 7. So therefore, h of x is not continuous at a. Now, we basically can flip the argument on its head in part B when we're looking at irrationals. If you're looking at irrationals, the value of the function is 23. So again, in this case, B is irrational. But the problem is, again, the function is giving you a value of 23 at B, but no matter how close you are to B, you can still find rationals. Again, in both parts of this problem, fundamental is the fact that between any 2 points, you can always find irrationals, and you can always find rationals. So, no matter how close you stay to B, there are going to be some rational numbers, and they give you a value 16 units away. So no matter how close you stay to B, you're still getting values 16 units away. You can't get arbitrarily close. So to slightly adjust the argument, let epsilon equal 1. Again, as long as I take a number less than 16, I'm fine here. So let epsilon equal 1. For any choice of delta greater than 0, there will be a rational x such that the absolute value of x minus b is less than delta. That is, no matter how small delta is, there's always going to be a rational number within delta units of b. So that says when you compute absolute h of x minus h of b, this rational number x is giving you a value of 7. This irrational number b is giving you a value of 23. These are 16 units apart, which is significantly bigger than the number 1, which is epsilon. So again, if epsilon is equal to 1, you can't find a small interval that keeps all the values of your function within 1 unit of 23, because no matter how small a number you take here, there's a rational number sufficiently close to b that makes the function equal to 7. So that takes care of 3, A and B. Let's move on to, see, this is going to be page 11 of the notes. Problem 8. Explain why there's a point in the interval 0, 1 such that x e to the x equals x plus 1. Well, notice when you plug in 0, this gives you 0 and this gives you 1. So the right-hand side is bigger. When you plug in 1, this gives you e and this gives you 2. The left-hand side is bigger. So we went from this being the bigger one to this being the bigger one. And as we said in a problem before, if you have 2 continuous functions and you switch the role of bigger and smaller, you can look at the difference, and the difference changes sign. So let h equal x e to the x minus x plus 1. If we study this on the closed interval 0, 1, we observed here that h of 0 is negative 1, so it's negative. H of 1 is e minus 2, which is positive. So on this interval, h is continuous and changes sign. This should be a familiar theme for us. So if you have a continuous function that changes sign, then the intermediate value theorem says that there exists a point on the interior. That's the open interval. There exists a point in the open interval 0, 1 such that h of c is equal to 0. But h of c being equal to 0, so that says c e to the c minus c plus 1 is equal to 0, or it says that c e to the c is c plus 1, which is exactly what we want. There's some point in the interior that makes this function equal to this function. So again, this is like the 3rd time we've come across this idea. If you have 2 continuous functions and they switch the role of the larger and the smaller, then if you look at their difference, the intermediate value theorem is going to say at some point their difference is equal to 0. And if at some point the difference is equal to 0, that means the 2 functions were the same. And again, for number 9, same sort of reasoning. Between 1 and 2, the functions switch roles between which is the bigger and which is the smaller. Okay. Moving to number 10 from the additional homework problems. Okay. This is really a good math 611 problem. Consider x cubed on the interval from 0 to 2. Find the formula for the upper sums in terms of n used to compute the integral from 0 to 2 of x cubed when 0 to 2 is divided into n equal subintervals. Take your limit and compare it to the answer you get using the fundamental theorem of calculus. So here we go. We're looking at x cubed on the interval from 0 to 2. And we're going to break it up into n equal pieces. So each piece, since the entire interval is of length 2, each piece is of length 2 over n. Now, since this is an increasing function on each interval, the upper sum comes from the right-hand endpoints. If you look at the right-hand endpoints, this is 2 over n, 4 over n, 6 over n, etc. Notice the first interval ends at 1 multiple of 2 over n. The second interval ends at 2 copies of 2 over n. The third interval ends at 3 copies of 2 over n. So in other words, x sub I, which is the right-hand endpoint of the ith interval, is I copies of 2 over n. And since this is an increasing function in computing the upper sums, you're always going to use the right-hand endpoints. So, if we want the upper sum, we'll call it upper of n, it's the sum of you plug the right-hand endpoints in and multiply by delta x. But the right-hand endpoints are I times 2 over n, and the function is x cubed. So it's I times 2 over n, which is going to be cubed. So I times 2 over n is going to be cubed. Multiplied by delta x is another copy of 2 over n. And let's see what we can factor out here. You've got 2 cubed times 2, so that's 16. You have n cubed times n, that's n to the 4th, times the sum from I equals 1 to n of I cubed. But this is the reason that you were given the formula that the sum from I equals 1 to n of I cubed is n over n plus 1 over 2, the whole quantity squared. So let's simplify. There's an n squared here and an n to the 4th down there. So that's just going to be an n squared. We still get n plus 1 squared. We still get 2 squared, which is 4. 16 over 4 can cancel. So this turns into 4 n plus 1 squared over n squared. So that's the upper sum you get, breaking this into n pieces and looking at the upper sum, which in Math 611 you call the right-hand sum. Again, increasing function means the upper sum and the right-hand sum are the same. So the integral from 0 to 2 of x cubed is the limit as n goes to plus infinity of the upper sums. Notice this is a quadratic leading term n squared. This is a quadratic leading term n squared. That means this approaches n squared over n squared or 1. The 4 is still here, so the limit is equal to 4. So by computing the integral in terms of upper sums, get an answer of 4. And now if you use the fundamental theorem of calculus, an antiderivative of x cubed is x to the 4th over 4. We evaluate between 0 and 2. You get 2 to the 4th over 4 minus 0 to the 4th over 4. And we just get an answer of 4 minus 0, or 4. So the answer from the fundamental theorem of calculus and the answer we get from looking at limits of upper sums, in both cases we get an answer of 4. Okay. Final two problems are 11 and 12. So this is page 13. And 11 and 12 are very, very similar. Okay. In 11, we have f of x is 7 when x is rational, but it's 11 when x is irrational. And we want the upper sum to approximate the integral from 5 to 20 of f of x dx. And we're also going to want the lower sum. Well, here's the point. Let's look at the interval from 5 to 20. And you break it up into n pieces. Well, if you're computing the upper sum, on every one of these pieces, there will be irrational numbers. So for every piece, the maximum value is going to be 11. Because again, on every piece, you're plugging in rationals and irrationals. The biggest value you get is 11. So when you're computing upper sums, on every piece, you're getting a value of 11. So the upper sum is actually a rectangle, height equal to 11, width is equal to 15. Because again, as opposed to, say, the previous problem, on different intervals, you get different values for the maximum, or for the upper sum. But here, every single interval you take, the maximum value is 11. So when you approximate the integral by rectangles here, every little rectangle here, because again the upper sum can be a bunch of rectangles, every one of them has a height of 11. When you add all this up, you get 11 times 15, or 165. So no matter how many pieces you take, the upper sum is 11 times 15. In the same way, the lower sum, on every subinterval, you're going to find a rational, which means you're going to get a value of 7. So for every single interval here, the minimum value is 7. So the lower sum is a bunch of rectangles where the height is equal to 7. When you put them all together, you get a big rectangle of 7 by 15. 7 times 15, I think, is 105. So, no matter what n is equal to, you get an upper sum of 165. No matter what n is equal to, you get a lower of 155. Well, if the integral exists, the limit of the upper sums and the limit of the lower sums need to be the same. But since every single upper sum is 165, if you take the limit, you get 165. Since every lower sum is the same, when you take the limit, you get 105. Notice these are different. Well, if the integral existed, these two numbers would be the same. But since these numbers are different, the integral doesn't exist. Almost the same type of reasoning for number 12. I'll go to another page, though. I think it's page 14. I think it's problem number 12. We're looking at the function g of x on the interval from -2 to 14. You're going to break the interval up into n pieces to approximate the integral. But when you're doing upper sums, on every single subinterval, you're going to find a rational point. The rational numbers give you values of 15. On every single interval, you're going to find irrational numbers, and the irrational numbers give you values of 3. So when you're computing the upper sum for each subinterval, the biggest value is 15. So in this subinterval, height of 15. On this subinterval, height of 15. You get a height of 15 on every single subinterval. So again, look at it this way. You take the interval from -14, you break it up into n pieces. On the first piece, the maximum is 15. Second piece maximum is 15. Third piece maximum is 15. Why? Because on every piece there's a rational number, and rational numbers give you values of 15. So the upper sum is you have a whole bunch of rectangles whose height is 15. When you put this all together, you get one giant rectangle whose height is 15, whose base is 16. So the upper sum is 240. For the lower sum, on every single subinterval, there's an irrational number, and irrational numbers give you values of 3. So the lower sum is just going to be one rectangle of a height of 3 and a base of 16. So no matter how many pieces you break this up into, the upper sum is 240, the lower sum is 48. So if you take the limit as n goes to plus infinity of the upper sums, you get 240. If you take the limit as n goes to plus infinity of the lower sums, that's equal to 48. If the integral existed, you could take limits of upper sums or lower sums. But these give you different answers in this case. So, if the limit of the upper sums and the limit of the lower sums give you different answers, that tells you the integral doesn't exist. Again, why for these two problems do the integrals not exist? Because the functions are badly not continuous. I will post all of these sheets online, but my job now is to make sure that I can properly post up this session. So I hope you found it helpful, And any questions or issues, just get back in touch with me. Thanks.